So welcome all. We will cover process variables and their classification, go into the details of process variables and their classification for purposes of control. That's the agenda for today's lecture. As we saw last time, process variables are classified into input process variables. The input process variables are causal in nature, and the output process variables are affected by the causal variables. Input process variables are further classified into control inputs or manipulated variables or disturbances. Manipulated variables are inputs to the process that we can adjust or a controller can adjust. Disturbances are input process variables that are what they are not adjustable. We also saw that a manipulated variable with a strong effect on a process variable can be used to adjust itself in such a way that the process variable ends up close to a desired value, a set point. This is the idea behind control. And so what you have are processes with a limited number of control degrees of freedom, manipulated variables, a very large number of measurements, and n number of disturbances or r number of disturbances. We have usually n is fixed and small and usually can't be changed. M is large and it's cheap enough to install extra sensors to measure extra things these days because of technology. So M is much greater than N. Output process variables are many. You can also combine them so that they give you more meaningful information about the process. Manipulated variables, on the other hand, are limited by the process design, and so you need to be wise in terms of how these manipulated variables are used for regulating or controlling the process. You got to be very careful in choosing what you control and how tightly you control it. Now, just to fix ideas on input process variables, output process variables, and so on and so forth, let's take a very simple liquid tank. So what you have is a liquid stream coming in. The tank is filled with liquid and there's a stream going out. You got a flow sensor on the inflow stream, you got a flow sensor on the outflow stream. Fi means flow indicator. Then you have a level indicator and you also have a tank temperature indicator. The valve position of the inflow stream and the valve position on the outflow stream, these are specified by the user or the operator. So what you have as process variables, you have the position of the F in valve, you have the position of the F out valve, then you have the flow in and the flow out, volumetric flow in and the volumetric flow out, F in and F out. You've got tank temperature, you've got tank level, F in, F out, T tank and level tank are measured, but then you also have the temperature of the stream coming in, the temperature of the stream going out, etc. as process variables. T in, T out are not measured, but nevertheless they are process variables. Now, of these process variables, you can see the input process variables are what is being input by the operator. Those are the position of the valves F in and F out, position of F in, position of F out. There's also the temperature of the inlet stream. This position of F in and position of F out, this actually determines what the flow in would be and what the flow out would be. Yeah, so these are input PVs. The output PVs are consequence or affected by changes in the input PVs. Yeah. So if you change position of Fin changes. If you change position of Fout valve, Fout changes, and so on and so forth. So the output PVs are, and in response to these changes, the level changes. If temperature of the inflow stream changes, T in changes. You could also include other process variables such as the ambient temperature, which determines the heat loss across the tank, which in turn affects the temperature of the liquid in the tank, and so on and so forth. So output process variables are Fin, Fout, T tank, level of the tank, T out. Notice that the output process variables are affected by changes in the input process variables. The user is specifying, or the operator is specifying, the valve position of the Fin valve and the valve position of the Fout valve. Is there anything been manipulated to control something? Right now, no. So there are no MVs in the sense of control. There are no manipulated variables in the sense of control. Here I saw an intermediate situation, an altered situation, same process, but now what you have is a flow controller that measures the inflow Fin. The flow controller compares it with the desired value of Fin set point, the desired value of Fin, which is Fin set point, and then it adjusts the valve position POS Fin. Yeah, so you got a flow controller on the inlet stream. You also have a flow controller on the outlet stream, and then you have the desired value of Fout, which is denoted by Fout set point. Set point. Okay. So in this case, what are my process variables from the perspective of what the user is specifying? All previous process variables here, they go here, but then the user is now specifying Fin set point and Fout set point. So these are additional process variables specified by the user. Notice that now user is specifying Fin and Fout set points, and the respective flow controllers are adjusting the valve positions. Yeah. So the valve positions are not being specified by the user. In fact, these are now calculated variables or dependent variables or affected variables. Yeah. So the input process variables are Fin set point, Fout set point, and T in. The output process variables are all that was there previously in this situation, plus the controller is now effecting changes in the valve positions on the in stream and in the out stream, and so these valve positions are affected or output process variables. See, because of the control that we have implemented, what constitutes an output process variable, what constitutes an input process variable, that set has changed. What is being specified by the operator? The specification by the operator is Fin set point and Fout set point. These are the two things that the operator is specifying, and in this specification is being affected by the controller by manipulating the valve positions, inflow and outflow. So the manipulated variables are position of the inflow valve, position of the outflow valve. Yeah. So you see, when you implement a control system on a process, you are effecting new relationships between the process variables through the controller, and that changes what constitutes input process variables, what constitute output process variables, what is specified, what is calculated, or what is independent, what is dependent. Yeah. Here's what you are likely to see in a plant. What you have here is a flow controller. The inflow controller is there, the outflow controller is there, but now you have a level controller that is adjusting the F out set point, and the level controller set point is specified by the operator, and we'll call it what, LVL? Yeah, LVL set point. This is being specified by the operator, and of course you've got the temperature indicator. So in this case, what are my process variables? Everything before are process variables, but now you also have level set point, which is additionally being specified by the operator. Yeah. Input process variables are three only: the flow in set point, the level set point, and temperature in of the in stream. You could also have, for example, temperature ambient, and this remains there. Ambient temperature, this would be there on every. That's also an input variable in the sense that it affects the heat loss and hence the temperature of the liquid in the tank. So these are input process variables. What are the output PVs? Previous meaning these guys, plus, you see, this set point is being calculated by the level controller. So this is actually a dependent process variable, an affected process variable, and therefore it is an output PV. What is being specified? Well, the operator is specifying again two things: flow in and tank level set point. Notice, regardless of the situation and the control system, the operator is specifying always two things. Here it is the valve position, here it is F in and F out set points, and here it is F in set point and level set point. Okay, so this was a very simple example which highlights the key aspect of how a control system changes the relationships between process variables, and these changes in the relationships reflect in what constitute input process variables, what constitute output process variables. When you implement a control system, the set of input and output process variables changes compared to no control. And as the control system gets more and more complex, you keep on adding more process variables in the matrix, in the mix. All right, let's look at somewhat. Oh, by the way, this I forgot. In order to hold F in set point and level set point, the inflow valve position and the flow out set point are being adjusted. Now let's look at a somewhat more complicated example. This is a flash drum. You've got a hot stream flowing in through a valve. The valve does some pressure drop. There's some pressure drop across the valve, and you are heating the tank, and because of the heat and perhaps the feed is already partially vaporized, so you have vapor stream leaking, leaving the process V out through the V out valve, and hot liquid leaving in the L out stream. You've got the temperature and level measurements on the tank. You've also got flow measurements on the outstream, liquid outstream, on the inflow stream. Vapor streams usually do not have a flow measurement, but you have a pressure measurement on the tank. The tank pressure and the line pressure are going to be the same. So in this situation, what are my process variables? Key process variables is what I would say. So you got the position of the four valves, F in, V out, L out, and the steam valve. Let us say you're heating using steam. You've got the flow in rate V out rate, L out rate, and the heat transferred to the liquid. You've got the composition of the feed, composition of the liquid out, composition of the vapor out. You got the temperature of the tank, you got the level of the tank, you got the temperature of the feed coming in, you got temperature of the vapor that's leaving the tank, you got the pressure of the tank, etc. There's all kinds of process variables. Now which ones are input PVs? And input PVs are, the operator is specifying these things: temperature of the feed in, pressure of the feed in, composition of the feed in. I'm calling it Q loss, but this should actually be T ambient, because T ambient is what determines how much the loss is. The colder the ambient, the more the heat loss. So Q loss is the heat loss across the tank. So instead of Q loss, T ambient would be a better process variable. Q loss is a output process variable. T ambient is an independent process variable, and hence it's an input process variable. Output PVs. What are the output PVs? The flow into the tank. See, when you change the valve position, the flow in changes. So flow in is an affected variable, and hence it's an output PV. Pressure of the tank, temperature of the tank, level of the tank, liquid out, V out, and so on and so forth. These are output process variables. What are the things that are being specified by the operator? Well, the valve positions, the 4 valve positions. Is anything being manipulated here? Right now, nothing. So there are no control manipulations. So we'll just say none. Now let's implement a simple control system. And the simple control system is shown here. So what you have is the steam valve position is fixed by the operator. You got a flow controller on the stream going in. If the pressure in the tank increases, that means you're generating more vapor than is leaving. So if the pressure increases, let the vapor out, and the vapor is let out under pressure control. So the pressure controller, if more vapor is being generated, pressure would increase, and the pressure controller would open this steam valve, this vapor out valve, V out valve. Okay, so you got a pressure controller adjusting the V out valve. Then you have a flow controller on the L out line, on the L out valve, and a tank level controller that adjusts the I think it is L out set point. Okay, so the level controller is adjusting the L out set point. So in this case, what are my process variables? Well, everything from here goes here. Additionally, because of the control loops that I have implemented, operator has to specify flow in set point, pressure set point, level set point, position of the Q valve. Well, this was already there, but so this need not, because this is included in previous, so this need not be included again. L out set point, that's an additional variable because of the flow controller that you have. So these are additional process variables because of the control system that has been implemented. Of these, what are the input process variables? Well, the operator is specifying these things, so these remain input process variables. Temperature of the feed in, pressure of the feed in, ZF in, Q loss, these things of course remain there. But notice that input PVs has shifted from valve positions to the set points because of the controllers. Output PVs, flow in controller adjusts position F in. So position F in is a dependent variable. It's an affected variable. It is changed in response to changes in flow in or F in set point, and by the action of the flow in controller, and therefore it is an output PV. Similarly, for similar reasons, this is also an output PV, this is also an output PV, this is also an output PV, and I can also add L out set point to it, because this set point is being calculated by the level controller. Yeah, so this is also an effected process variable, and therefore this too should come in the list of output process variables, effected process variables, dependent process variables, calculated process variables. What is the operator specifying? Four things: the set points of the controllers: inflow set point, tank pressure set point, tank level set point, and the steam rate set point or steam valve position set point or position. What is being manipulated? This is being manipulated, this is being manipulated, this is being manipulated. This of course is a direct operator specification. So at the end of the day, whether you're looking at this situation or you're looking at this situation, notice that there are four specifications by the user. When there is no control, the user is directly specifying the valve position. When there is control, the user is specifying the set points. Now let's look at a distillation column. This will take some time, so bear with me. You got flow going in, you got sensors, temperature sensors on the various trays telling you the temperature on that tray. Look at the valves. You got reflux flow measurement, distillate flow measurement, reflux drum level, condenser pressure, inflow measurement, bottom level measurement, bottom rate measurement. These are all measurements that you have. You also have tray temperature measurements, which I already described. There are a total of 6 control valves: 1, 2, 3, 4, 5, 6. And when you have no control, these valve positions are being directly specified by the user. So what are my process variables? The 6 valve positions: inflow rate, reflux rate, bottoms rate, distillate rate. These are indicated by, these are process variables, and these are also measured. The heat removed in the condenser, the heat given in the reboiler, the heat lost to the ambient, feed composition, temperature of the feed, pressure of the feed, pressure of the column, temperature of the trays, distillate mole fraction, bottoms mole fraction, level in the reflux drum or condenser, level in the reboiler, etc. There's all kinds of process variables. What are my input process variables? Fin, oh, this is not correct. Actually, these should be my input process variables. These are my input process variables, and then of course this is also input process variable. So this guy should go. What are my output PVs? All the flows that are measured, column pressure, the levels, temperature of the trays, these are all output process variables. In fact, XD, XB, everything that is not an input PV is an output PV. Let's put it that way. So I think there will be an etc. here. What is the operator specifying? The 6 valve positions. Is anything being manipulated? No. So there are no manipulated variables. This is a no control kind of system. Now let's implement a control system on this. The temperature measurements, level measurements, etc. are there. So what you have is, you have a flow controller on the feed stream, you have a pressure controller on the condenser, you have a level controller on the reflux drum which adjusts the distillate rate, flow controller set point. Similarly, you have a level controller, bottom sump level controller, which adjusts the flow set point of the bottom stream. You also have a reflux flow controller and the set point of this reflux flow is kept in ratio with the feed to the column inflow. So what you have here is L by L indicates reflux, L by F set point. This is specified by the user. So you have this flow, you multiply this by L by F, and therefore you get the reflux flow rate set point. Okay. And then you have a flow controller on the steam valve, and this flow controller receives a set point, a steam flow set point, a Q reboiler set point from the temperature controller. By maintaining tray temperature, you indirectly control composition, you indirectly maintain the split. To understand this, suppose light key starts dropping down the column, then the tray temperature will start to drop. If the tray temperature drops, the temperature controller increases the steam, reboiler becomes hotter, vapor rate goes up, and the light key that is dropping down is then sent back up. So in this way, the light key is prevented from dropping down the bottoms, and you get indirect composition control. Okay, so in this situation, given this control system, what are my process variables? Everything before plus all the set points due to the controllers that I must specify. And note that the level controller, for example, is specifying or is fixing this. This is LSP. This level controller is fixing the distillate flow rate set point. Okay. So all the set points due to the addition of controllers, these are additional process variables. What are my input process variables now? Well, the user is specifying the set points of these controllers, and of course there are other process variables, but you've got the temperature of the feed, the pressure of the feed, because the pressure of the feed determines its quality, how much of it is vapor and how much of it is liquid. The composition of the feed. Instead of Q loss, I would prefer T ambient, because T ambient is what determines the loss of heat from the column. Yeah. What are my output PVs? Output PVs are everything that is calculated by the controllers. So this QR set point is calculated by the temperature controller. This set point LSP is calculated by the ratio controller, reflux to feed ratio controller. This set point DSP is calculated by the reflux drum level controller. This set point bottoms flow rate set point is calculated by the bottom sump level controller, and of course the valve position themselves. Yeah, so these are all output process variables, dependent process variables, affected process variables, affected by action of the controller. What is the operator specifying? He is specifying the set point of the 6 controllers that we have, and in order to do so, these are the manipulations that are occurring. Position of the feed valve is, yeah. Oh, this is not FSP, this should be LSP. This is what is being manipulated. So this guy is held by this guy is held by that guy. Yeah, 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 yeah. Okay. So these are the manipulated variables. So this is a distillation column. Again, the point to be noted is when you implement controllers, your set of input and output PVs changes. In fact, the output PV, the number of PVs expands because now you got to specify additional set points, and what was previously an input PV becomes an output PV because the controller is now adjusting that input PV, making an adjustment to that input PV. Let's look at a toy process. This one is going to, let's count the number of valves first. 1, 2, 3, 4 plus 5 valves on the column, so there's a total of 9 valves. What is the process? You're feeding fresh A to the process and it is mixing with the recycle stream, recycle A. It is passing through a feed effluent heat exchanger. The cold feed stream recovers heat from the hot reactor effluent, and the preheated reactor feed stream is then heated to the reaction temperature in this reactor heater. The reaction A goes to B, occurs in the reactor. Let us say it is exothermic and the reaction heat is removed by jacketed cooling. The reactor effluent is a mixture of A and B. It loses heat in the feed effluent heat exchanger and then it is sent to a column, and let us say B is heavier than A, so heavy B drops down the column. You require pure product B down the bottoms. Nearly pure A is recovered up the top, and this unreacted A is recycled. So this is the process. You got flow measurements on all streams. So you got a flow measurement here, 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 you got a flow measurement here. So these are flow measurements. You got the reactor level, the reflux drum level, you got the bottom sump level, you got the column top pressure, you got the column bottom pressure, you got tray temperature measurements, you got the reactor temperature, you got the, this is the jacket temperature, sorry, this is the jacket temperature, you got the reactor temperature, and then you got the reactor feed temperature. These are all measurements. You also have the temperature of the cooled stream going into the column, and so on and so forth. I mean, this is just an example. So what are my specifications? What is being specified by the operator? The operator is specifying the valve position of all the valves. There are a total of 9 valves we counted. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So these 9 valve positions are being specified by the operator. In addition, what are the other process variables that we have? Output process variables that we have are the flow, the fresh feed flow, the heat transferred in the heater, the heat removed in the reactor, effluent flow rate, reflux rate, distillate rate, bottoms rate, the heat transferred or removed in the condenser, the heat given in the reboiler, reactor inlet temperature, reactor temperature, jacket temperature, level in the reactor, temperature of the stream going into the column, pressure at the top of the column, pressure at the bottom of the column, temperature of the trays, level of the condenser, level of the reboiler, and so on and so forth. These are output process variables for this system. There are many other process variables such as T ambient. So there are many other process variables, T ambient, for example. These are input PVs. Maybe there is a solvent that is coming along. Maybe this is the fresh feed is actually fresh A plus a solvent, and the solvent is heavy, so product B and the solvent leave out the column. Then you also have the composition of this stream, which is an input process variable. Yeah, but the bottom line is this is what the process is. There are many process variables. We have just listed the important ones. T ambient is actually an input process variable. Now let us implement a control system. So what we have is the feed valve is manipulated in order to hold the fresh feed flow constant. The QHTR valve is adjusted to hold the reactor inlet temperature constant. That's what this guy is. On the reactor, you have the temperature of the reactor, a reactor temperature controller manipulates the jacket temperature set point, or fixes the jacket temperature set point, and the jacket temperature controller, this guy, manipulates the coolant flow in order to deliver that jacket temperature. So you can imagine, if the reactor temperature is increasing, the reactor temperature controller will say reduce the jacket temperature, and the jacket temperature controller will then bring in more coolant in order to reduce the jacket temperature. And as the jacket temperature is reduced, more heat will get transferred across the valve, across the walls of the reactor. As more heat gets removed across the walls of the reactor, the increasing reactor temperature will hopefully come back. So that's the idea behind this control system. You've got a level controller setting the effluent flow set point, E set point, and the effluent flow controller is adjusting the E valve position. As before, you got a pressure controller, level controller, reflux drum level controller, bottom sump level controller, reflux maintained in ratio with the feed to the column, and the reboiler duty being adjusted in order to hold a tray temperature. This is the same control system as we saw for the single distillation column previously. So now what is being specified by the operator? Operator is specifying the 9 set points: fresh feed flow set point, reactor inlet temperature set point, reactor temperature set point, reactor level set point, reflux to feed ratio set point, this guy, this is L by F set point, pressure set point, this is P, level of the condenser set point, level of the reboiler set point, controlled tray temperature set point, this guy, T, tray set point. Yeah. What are my output process variables? Everything previously plus all valve positions which are adjusted by controllers, plus any set points that are being adjusted by master controller. So for example, reactor temperature controller adjusts the jacket temperature set point. Reactor level controller adjusts the effluent flow set point, reactor effluent flow set point. Column tray temperature controller adjusts the reboiler steam flow set point. Bottom level controller adjusts the bottom flow set point. Reflux drum level controller adjusts the distillate flow set point. So these are all output process variables as a consequence of the controllers that we have implemented. So we have looked at a toy process. Now as an exercise, I would like for you to identify and classify the relevant process variables into input PVs and output PVs. And let's look at the process. So you've got a vapor phase packed bed reactor which is cooled. So you've got feed flowing into the reactor. The feed is cold. It is brought to the reactor temperature by a heater. Exothermic reaction occurs in the packed bed reactor. Reaction heat is removed by cooling, that is indicated here. The hot reactor effluent is cooled in a cooler, that's here, and it is cooled so that it condenses. The liquid is collected and the liquid is flowing out as a liquid outflow from the tank. Any uncondensed vapor leaves the tank as vapor. So this is the process. This is the no control where the operator is directly specifying the valve positions. So what are the process variables for this case, and classify those process variables into input process variables and output process variables. Here we have a control system implemented. And what we have is a flow controller on the feed. Reactor inlet temperature is controlled by adjusting the heater duty over here. Reactor temperature is controlled by adjusting the reactor cooling duty, that's over here. The cooled reactor effluent temperature is controlled by adjusting the cooler duty over here. The vapor leaves the tank under pressure control over here, and the liquid leaves the tank under level control over here. So this is the simple control system that has been implemented on this process. What are the process variables, input and output process variables for the system with control, for the system with no control? Please do this as an exercise, and this brings us to the end of this lecture. To summarize, what we have seen is that there are several process variables in any process, and these process variables may be causal meaning input process variables. Manipulated variables and disturbances are causal process variables, or these may be affected or output process variables. There are potentially infinite output PVs, as many output PVs as sensors you have, and some of these output PVs may be controlled by manipulating the MVs. The number of MVs in a process is fixed and limited, and therefore this limits the number of output process variables that can be controlled. So because of this limitation, I would like the world, but that is, I have what I have and I don't have what I don't have. I would like knowledge about everything, but I know what I know and I don't know what I don't know. Yeah. So you got to make do with what you have. So what you have are a limited number of manipulated variables. How best to use them? Their best use occurs when what is controlled is chosen wisely, because you don't have the liberty to control everything that you want. You can only control so many things. And to make that choice wisely, like I said last time, process understanding is key. You got to understand your process well. You got to understand the context in which the process is supposed to operate, and once this understanding is there, designing a control system is actually quite straightforward. And I hope you also saw that a control system creates new relationships between PVs, and these new relationships get reflected in your set of input and output PVs changing. If you have a set of input PVs and output PVs with no control, as you keep adding controllers, some of the input PVs become output PVs because they are adjusted by the controller, and your set of process variables keeps on growing. So the classification of the process variables depends on the control system implemented. And a control system creates these new relationships, and these new relationships, like we discussed last time, alter the dynamic characteristics of the process by transforming variability from the CVs, controlled variables, to the MVs. With this, we come to an end of this lecture. Hope to see you next time. Thank you for your attention, and goodbye.